Hello, class. This is a recorded lecture for section 5.3 in our trig textbook, and I think we're all happy this will be the last one, last section. Personally, I think this is an important section. This is this idea of taking a trig representation for complex numbers. And you'll see that when we do this in calculus, for those of you heading to Calc 2, you'll get a big review of this again, and you'll talk about different forms of this type of representation as well. And the reason why we do these transformations again is because when you do a transformation from, say, coordinate of, rectangular to polar, you would see that the equations are easier when we have curvy lines. And so the reason why we go from the rectangular version of complex numbers to the what you would consider trig, or sometimes called polar version of complex numbers, is some arithmetic is so much easier doing it in the trig representation or polar representation of complex numbers. So we're going to introduce that to you in this section. And personally, in the electrical engineering world, a lot of things are modeled with complex numbers. So I have definitely used this in my life and analysis. So to get started, let me pull up the slides here. And so you can see here we have the section 5.3. And we're going to go through 4 different concepts. So we're going to introduce the complex graph. So the idea of graphing a complex number, and then the polar form of complex numbers, and then these 2 theorems, which are the reason why we do this transformation to begin with. You'll see multiplication and addition and taking things to the roots or to the power is really so much easier in the polar or trig representation of complex numbers. And you'll see that addition and subtraction is so much easier in the rectangular or the what you would consider the original version of our complex numbers. So let's introduce the graph. And so this is going to be a 2-dimensional graph. If you think about real numbers, right? We had real numbers where you would just have computer running a little slow today. So if we just deal with the real number line, right? This would be the real number line, where here would be 0. And if you went to the right, it would be positive. And if you went to the left, it would be negative. And so what we're adding here now is we're going to add a vertical axis to the number line here. And it would look like this. So this would be the real part. And then this would be the imaginary part. And if you remember, we're going to use the letter Z for complex numbers. And we had a real part plus imaginary part. And so if you think about how we would do the scales, again, the X or the real number line here is exactly the way it was before. That would be 1, 2, 3, 4, and then -1, -2, -3, and -4. Excuse me. So the complex number line, again, similar, but these would be i's. So again, up is positive, and down would be negative. So that'd be -I, -2i, -3i, -4i. So if you wanted to say plot one of these. Let's pick a couple to plot. So let's pick, let's see, let's do the first one in green. So let's call this Z1 and let's plot 2 plus 3i. So just like you think you would do it, it's the way you do it. So that's the good news. So you would go over 2 on the real, on the positive, and then up 3. So that would be right here. So if we did another one, say Z2, and let's do 3 minus 2i. So if you did that one, it would be, again, 3 here, and then minus 2i, you would go down, and it would be right here. And what you'll see is that when you add and subtract complex numbers, it is so much easier to do in this form, which is we'll call the rectangular form for complex numbers. And the idea is just like we did in our complex number review, you add the real part, right? And then you add the imaginary part, right? So if you did that, you would get 5 plus I. And let's graph that one, say, and this pink. So that would be 5. So we need one more here. And then I would be right here. So adding, subtracting, you'll see that we're going to definitely do it in the Cartesian style representation of a complex number. When we talk about a multiplication and especially division, it is easier to do in the polar form or the trig form. And you'll see that calculating roots or taking a complex number to a power, way easier to do in the trig form than it is in the rectangular form. Okay, so another thing that we want to introduce is this idea of what they call in math as a modulus. And the way that we talk about this concept is the modulus is defined as the distance of a complex number from the origin of the complex plane. So sometimes, if you remember, we use this absolute value idea, right? So let's take a look at that. So say like we had an example here, do it maybe in yellow. Z equals, say, 2 plus 3i. All right, we had that one before. So 2 and 3i. Okay, so let's stick that point right there. I don't know if yellow is very good. So let's go back to green here. So basically, the distance from the origin to that point is defined as the modulus. And so how would you calculate that? Well, again, I think you're probably sick of this now, but old Pythagorean's theorem, right? So if you think about what we have here, this is the hypotenuse of the right triangle that looks like that. And so if you think about this, in this calculation, it would be 2 squared, right? Plus 3 squared. So 2 is the real part. 3 is the imaginary part. And then you would take the square root of it, right? That would be our R value. And so that's the same calculation here, except when we define it, we're going to use the A's and B's. So we define it as this way. A squared plus B squared. And for those of you that are really thinking about this now, you could say, oh, that's the R value in the polar coordinate system, right? And the answer is yes, it is. So you'll see that when we do representations of complex numbers in the polar plane or the trig representation, you'll see that's what our R value will be for that representation. So just to finish this, that would be what? Square root of 13, 649. Yeah, so that would be square root of 13. So let's do another example of, say, calculating the modulus. So if you're calculating the modulus, let's pick, let's do the pink one again. Let's say we do 8 minus 5i. And so it's a little bit hard to graph an 8 here since my scale isn't that big. But how do you calculate the modulus? And the modulus is usually indicated by the absolute value of z, or you would do the absolute value of that whole number. And again, if you think about that, it's going to be 8 squared and then plus a minus 5 squared. So if we keep doing that, let me see if I move this up a little. There we go. So if we keep doing that, you would get 64 plus 25, and we need our square root. And so that would be square root of 89. And again, that is the distance from the origin to that point on our complex graph. So the next thing we want to do is formally introduce to you the idea of representation of a complex number, and they call it the polar form. Sometimes I call it the trig form, right? And so here is our axes. For real is the horizontal, and the vertical is the imaginary. And so if you had this point, complex number a plus bi, how would we represent that as a trig function, as in the polar plane? Well, I think r is pretty obvious, right? Or if you have this r, that's what we were calling the radius, right? Or the hypotenuse, and it's actually the modulus that we just talked about. And so that's defined as a squared plus b squared. So say like you wanted to define this angle as theta. Okay, now we have a right triangle, right? So let's talk about that. Hopefully the last time, right? And all these crazy right triangle conversations we have. So what would this one be? This distance A, right? Well, remember, this is adjacent, all right? So getting back to cosine, we would define this as cosine of theta, right? Would equal what? It would equal the adjacent over the hypotenuse. So if you do a little bit of algebra and bring the r to the other side, what does A equal? A equals r cosine of theta. So we could define A as r cosine of theta. And I bet you can guess what the B value is, right? Well, the B value, if you think about here's theta, this is opposite. So sine of theta is B over r. And so B, with a little bit of algebra, bring the r to the other side, would be r sine of theta. So here's our second equation, B equals r sine of theta. So again, if you think about how we set up our polar coordinate system, how would we define theta given A and B? Well, that would be tangent, right? Because that would be opposite over adjacent. So again, the last of the equations that you need just from our polar coordinate plane. And I hope you realize this looks just like this would be B over A. So if you remember our transformation, A was actually the X variable and B is actually the Y variable. And this is where the polar coordinate plane comes in, as a representation of complex numbers. And so the idea here is that we're going to convert them from one to the other and back and forth. We'll start with that. So let me just show you here as the computer goes slow. Let me show you the representation. So here's our definition. So our definition is given a plus bi, that we are going to have the r value equals square root of a squared plus b squared, and tan of theta is b over a. And as I stated before, a equals r cosine of theta, and b equals r sine of theta. So to finalize our representation, if we have z equals a plus bi, what do we do? Well, if we plug in what we have for a, we would have a equals r cosine of theta plus, what's b? It's I r sine of theta. And sometimes what you would do is pull out the r's, and the final representation typically looks like this: r cosine of theta plus I sine of theta. And so that would be the polar or the trig representation of a complex number. And here's what it looks like in the slide. So here we have it here. So you'll see slides 13 and 14 will be kind of useful because it gives you the polar form of a complex number, which we're going to be using now. And so I think it's a good place to stop this first of the recorded lectures for section 5.3. And we'll continue converting numbers, complex numbers to the polar form, and show you how to multiply and divide in the next